question about this? I'm going to move on to something else. And I need to check the time. Let's see. Oh yeah, I have the time. Okay, so next paper I'm going to talk about is it's a more practical paper. It's called Deep Causal Feature Extraction and Inference with Neuroimaging Genetic Data. They have a different kind of IV setup here. So this is the IV setup you would see on the left-hand side. Perhaps genetic factors affect your brain health or whatever, right? And it affects your probability of developing Alzheimer's disease. And perhaps there's a confounder, perhaps, let's say, if you're in a happy marriage or not, it affects your brain health, also affects whether you get Alzheimer's, right? So the IV setup that they assume here is something else. They assume that genetic factors cause the brain health. But then you can measure, I mean, brain health is an abstraction, but there will be an image, literal image of your brain, MRI image. But there's a function of that that's perhaps low dimensional, and that's what matters for developing Alzheimer's disease. So brain image doesn't really matter, the features of the brain matters. And the question is, can we use neural networks to learn this mapping from the MRI image to the features of your brain? Okay? And the reason is that high-dimensional brain imaging data is actually not suitable for as treatment in the IV setting, so they make this assumption. They do make parametric assumptions still. They have this kind of regression setup still. And they extract causal features from brain MRI image using this functional mapping. Here are some loss functions. I'm not going to go too deep into detail, but based on some L2 error, they are able to extract some representation for solving this problem. Of course, there's no guarantee, there's no proof or anything, but it's something that seems to be reasonable in practice, perhaps, and this is one of those things where you take a perhaps shorter leap of faith, hoping that it will extract meaningful features for your problem at hand. There are many more interesting papers for which I do not have time, but definitely very rich space. Not just feature extraction, but in general, these intersections. So definitely I recommend you to check some of these papers. And I'm gonna move on to the next part. Any questions before I do? Okay, so next is going to be generator modeling. What does this really mean, right? So here is some justification or explanation. What is a structural causal model, SCM? A structural causal model is basically a collection of equations that are read as assignment operators. Right? Now, what we can do with neural networks is we can actually try to approximate these functions in order to simulate the full SCM. Okay? So if I could mimic each of these functions in the SCM, then I get myself a causal simulator. That should be powerful, right? But the catch is this is tricky because you don't really have access to all the variables that affect your system. For example, in the very simple case, X causes Y, even here, you typically have latent variable U. You don't have a latent confounder, but you have an exogenous noise variable that you do not get to observe. So the U here affects Y, right? So how can you hope to learn this function using neural networks because you don't have the inputs, you don't have all the inputs. Half of the inputs is missing. So trying to learn the true functions in the SCM is an impossible task. This much is clear. But maybe we can get away by choosing our own noise variables, right? Instead of the true exogenous variables. Maybe I'll say, okay, let me just use a Gaussian. Let me just use a uniform distribution, something. You can definitely do that, but can you guarantee anything? That's the question that we are interested in. And where does the need for neural nets come from for high-dimensional data? So this is actually another view that you can justify using neural networks. For example, if you have this kind of causal structure, COVID symptoms cause X-ray image, because if you get COVID symptoms, you go to the hospital, you get an X-ray image taken, and then you show it to the doctor, and doctor tells you, oh, you got pneumonia. So pneumonia diagnosis is caused by the X-ray image, because doctor looks at that. But maybe hospital location causes both the chance that you will get COVID and COVID symptoms, but also how good is your doctor to diagnose you properly with pneumonia. So if you look at the correct causal effect formula for this contour adjustment graph, you need to be able to estimate this P of x given C. What is P of x given C? This is the distribution, the probability or the likelihood of you observing this specific X-ray image, given that you have COVID symptoms. There is not a large enough data set in the world that allows you to estimate this properly. So you can never hope to learn these explicit likelihoods from any size of data. And you can increase the number of examples. I'm not going to parse this again, but yeah, so this problem exists when you have high dimensional variables. You cannot explicitly learn the likelihoods. So one thing to argue here is that we know that deep generative models, such as GANs, diffusion models, whatever you want to use, deep generative models are really good at sampling from high dimensional distributions for whatever reason. Right? You can say it's the CNN, you can say it's the inductive bias, but they are good at sampling from these high dimensional distributions. The question is, how can we leverage, or can we leverage them to sample from interventional distributions? So maybe if I can do that, I'll be able to answer causal questions or perform causal inference. And here's the key idea of this chapter. A structural causal model sequentially generates your data based on the causal order. First you sample X, then you sample Y, given that X, and so on, right? That's why it's a DAG, directed acyclic graph. Each structural equation uses some observed and some unobserved variables that you don't have access to. But we can try to mimic this process using neural networks, regardless. So here's how it looks like. Here you see the real data generating process. I have a system. That system is obeys a set of structural equations that are hidden from me. I don't get to see them. But it generates data. And it also induces a causal structure. Okay? So now let's say you have access to the real data, a large real data set, and you have access to the causal structure, maybe expert knowledge. What we are going to propose, we are going to use a causal simulator. So I'm going to generate a fake X from some high dimensional noise that I will get to decide. I sample a high dimensional Gaussian, I feed it through a feed-forward network, and I call the output X, fake X. And I'll do the same for Y. I'll generate Y from some exogenous noise that I decide what it is, some Gaussian. Right? But when it comes to generating Z, I know Z is a function of X and Y. So what I need to do to simulate the causal process, I need to concatenate the fake X that I just generated with the fake Y that I just generated with another source of randomness, another high-dimensional Gaussian that I choose, and push it through another neural network, and I'll call the output Z. This is going to be fake Z. Now, what can I enforce here? I enforce the causal order. That's already done. But this is just generating nonsense, right? It's not really related to the real data generating process. What I can do is the following. So I can first observe that this neural network, let's say the random initialization of these neural networks, they can be summarized as a set of structural equations. So X is basically some function f prime of some noise E prime, which is actually NX here. Y is some function f prime of some noise E prime, another E prime that are independent. And Z is a function of X and Y and some other noise E prime. Right? So these look similar, except they are different functions. They are different noise terms. And from these equations, I'm obtaining fake data. I'm collecting fake data from my neural network that is not trained yet. What can I do with training? If I train this, I can sample from the real data distribution. So that would be enforcing the fake data distribution to be the same as real data distribution. Okay? So my promise to you here, if you can enforce this, good things will happen. And we're going to see what those good things are. And the question here is, how can we ensure P and Q are the same? Okay. So this is what we did in 2018 in causal GAN. So we proposed structuring the generator architecture of a GAN in terms of the causal structure. So it is going to act as a causal simulator. And then you also use a discriminator to align the distributions. So the fake data distribution that your neural network here, the generator, generates is going to be the same as the real data distribution. So this allows you to align the real and fake distributions. And if you have these two assumptions for this paper, causal graph is given and has no latent variables, it's a causally sufficient system, and distribution is strictly positive, the data distribution is strictly positive, then you can show that the optimal generator can be used to sample from any interventional distribution. And you can actually use this in a very simple image data set, where image is the sync node, and you have a bunch of other features. This is Celeb. And if this is the causal graph, then you can sample from interventional distributions. You can show intervening